Look around you. We're constantly surrounded by devices, tangled wires, and glowing screens. But we rarely pause to think about the invisible forces actually making it all happen. So in this explainer, we're going to completely demystify the core fundamentals of electricity: voltage, current, and resistance. We'll unpack Ohm's law and use a really handy visual analogy to lock these concepts in your brain for good.
You know, you probably plug your devices in half a dozen times a day without a second thought. But what exactly is traveling from that wall outlet, through the cable, and into your battery? It's not just one magic thing called electricity. It's actually a dynamic relationship between a few very distinct physical forces.
So let's jump right into Section 1. Meet voltage and current, the two fundamental concepts of electricity.
We're going to introduce the two main characters of our electrical story, starting with voltage. Think of voltage as the electrical pressure that pushes electrons through a circuit. Whether it's created by a tiny watch battery or a massive generator at a power plant, you can just think of voltage simply as the push. It's the driving force. Without voltage, the charged particles in a wire have absolutely no reason to move. They just sit there. Voltage is their motivation.
Then, on the flip side, we have current. While voltage is the push, current is the actual movement, the flow of those electrons through a circuit. If voltage is the motivation, current is the action. It's the physical progression of electric charge traveling from point A to point B to do actual work, like lighting up a bulb or spinning a motor.
Now, when we write this stuff down in the scientific world, we categorize these forces a bit differently. Voltage is represented by a V and measured in volts, which is super easy to remember. But current uses the symbol I for intensity, and it's measured in amperes, or amps for short. So when someone mentions a 9-volt battery, they're talking about the push. When they mention a 15-amp fuse, they're talking about the flow.
And here's where it gets really interesting, how they depend on each other. Voltage can exist completely on its own, even if zero current is flowing. Picture an open light switch. The voltage is sitting right there on the wall, just waiting. Current, however, flat out refuses to move without a voltage difference pushing it. And crucially, it needs a complete closed circuit to travel through. No closed loop, no current.
Because they play by such different rules, we actually have to measure them differently when testing circuits. To measure that push, we use a voltmeter connected in parallel across the components. But to measure the flow of current, we have to drop an ammeter right into the circuit in series. It literally has to be part of the flow path to count the electrons zipping past.
Which brings us to Section 2, the water pipe analogy, where we visualize these invisible forces.
Because we literally can't see electrons, let's use a water pipe analogy. This perfectly translates abstract math into physical stuff you can picture right now. Step 1. Voltage is your water pressure, like the heavy force in a water tower pushing down. Step 2. Current is the flow rate, how much water is actually pouring out the end. And Step 3 introduces our final element, resistance. Resistance is simply the narrowness of the pipe itself. Just think about using a garden hose. Changing the pressure or the pipe's size instantly changes how much water blasts out. If you have higher pressure, higher voltage, it pushes the water harder. More water flowing out every second means a higher current. But if you swap to a narrower pipe, meaning you increase the resistance, that restricts the flow, and your current drops. It's all one big balancing act.
Moving right along to Section 3, Ohm's law in action, and the math behind this relationship.
Ohm's law is what ties our three concepts together mathematically. Exactly like our water pipe, if you dial up the voltage, or the push, your current goes up, assuming the resistance stays exactly the same. Conversely, if you increase the resistance, like pinching that hose, it immediately decreases the current, assuming your voltage hasn't changed. They're totally linked. You change one, another has to react.
Let's put some real numbers to this to see how it works. Say you hook up a standard 12-volt battery to a resistor that gives you 6 ohms of resistance. The big question is, how much current is actually going to flow through this setup?
The math here is beautifully simple. By plugging these numbers into Ohm's law, we just divide the voltage by the resistance. So to find our current, we take our 12 volts of pressure and divide it by our 6 ohms of restriction.
Boom! That calculation gives us exactly 2 amps. With a 12-volt push fighting a 6-ohm restriction, you're going to get 2 amperes of current flowing through that closed circuit. And this math is universal. It applies whether you're looking at a tiny hearing aid battery or a massive city power grid.
Let's bring this into the real world with Section 4, real-life application, charging your smartphone. You probably have your phone sitting right next to you.
When you plug it into the wall, your charger acts as the power source, providing a steady 5 volts of pressure. Meanwhile, the phone itself communicates and might decide it needs 2 amps of flow to charge up optimally. The charger provides the potential, but the device actually determines the demand.
The key takeaway here? That 5-volt push is always there and stays constant. But the current, the actual flow of electrons, adapts perfectly to what the phone needs right at that second. If your battery hits 99%, the phone ramps up its internal resistance to draw less current, even though that 5 volts of pressure is still pushing from the wall block.
So, as we wrap up this explainer, if you remember absolutely nothing else today, lock in this stark contrast. Voltage is the push. Current is the flow. It's the difference between the motivation to move and the actual movement itself.
And of course, we can't forget the third player in our equation. Resistance will always be the force fighting against that flow. It's the opposition. It's the narrow pipe controlling the chaos, making sure our devices get the exact amount of electrical flow they need to run safely.
Think about this. Right now, all around you, your wall outlets are literally brimming with invisible electrical pressure, sitting perfectly still at the switch, just waiting for a closed circuit so it can flow. Next time you plug a cable in, picture that water pressure finally rushing through the pipe. So, with all that potential power sitting right at your fingertips, what are you going to plug in next?